What if I told you that some of the most powerful ideas in linear algebra come down to just a single number? No rows, no columns, just one cell. Orthogonal and unitary matrices are used to rotate, reflect, and preserve structure across multidimensional spaces. But how do they work when they shrink into the smallest form possible, a one-by-one matrix? What do they look like? What do they do? And why should we care? Let's look at the math inside one number and a tiny matrix and see how even the smallest matrices can hold interesting patterns. Orthogonal matrices are real and preserved dot products and norms. They're like rotation machines in real space. Unitary matrices do the same, but in complex space, using complex numbers to preserve inner products. Mathematically, a matrix A is orthogonal if the matrix multiplication of the transpose of A and A is equal to the identity matrix, while a matrix A is unitary if the matrix multiplication of the conjugate transpose of A and A is equal to the identity matrix. But what happens when your matrix has just one element? A one-by-one matrix is the simplest possible matrix. It contains just a single element. Visually, it looks like this. Its transpose is still the matrix having the solo element, which is the matrix A itself. And the one-by-one identity matrix is having 1 as the only element. By the definition of orthogonal matrix and our earlier observations, A is its own inverse. Putting this in the matrix property, A inverse equals the identity matrix I. We get a square equals I. And obviously, a square will be a one-by-one matrix with C square as its only element. So orthogonality means C squared is equal to 1, which further implies C equals 1 or minus 1. That's it. Just two possible orthogonal one-by-one matrices. Assuming these matrices define linear transformations, their effects can be illustrated graphically, such as how they act on vectors or reshape geometric figures. Hence, we finally get the identity matrix 1, which leaves any vector unchanged, and matrix minus 1, which reflects vectors over the origin. Unitary matrices allow complex values. In one-by-one form, we need the conjugate transpose of A, which is the matrix with C bar as its single element. If A is a unitary matrix, then its inverse is equal to its conjugate transpose. That is, a matrix whose only element is C bar. Then, by using the property A inverse equals I again, we obtain C. C bar is equal to 1, or mod C square equals 1. And finally, we obtain mod C is equal to 1. So, geometrically, C is right on the unit circle in the complex plane. It has a magnitude of 1. The unit circle is the set of all complex numbers with magnitude 1. Every such C can be written using Euler's famous formula, C equals e to the power I theta, which is equal to cos theta plus I sine theta. This form describes a point on the circle that's rotated counterclockwise by angle theta from the positive real axis. These include numbers like 1 and minus 1, which are also orthogonal. Then we've got I and minus I, which rotate vectors by 90 or 270 degrees. And of course, values like e to the power I pi over 4 and e to the power I pi, they represent phase rotations on the unit circle. Unlike orthogonal matrices, which only permit plus or minus 1, unitary one-by-one matrices allow infinitely many values, forming a smooth, continuous loop around the origin, like a rotating spotlight in the complex plane. Even though one-by-one unitary and orthogonal matrices may seem simple, just a single number, their structure reveals powerful principles, especially when generalized to larger systems. While orthogonal matrices exhibit the most basic form of symmetry in real space, reflecting or preserving orientation, unitary one-by-one matrices multiply by complex numbers of unit magnitude. Unitary matrices help in learning quantum bit manipulation, where phase shifts like e to the power I theta rotate qubit states without energy loss. In basic signal processing, a multiplication by -1 simulates inversion. As we dive into this topic, we begin to understand how orthogonality applies, even to something as simple as a one-by-one matrix. The one-by-one case is your portal into higher dimensions. Simpler doesn't mean weaker. It often means fundamental. And that's all I've got for you for now on orthogonal and unitary 1-by-1 matrices. Make sure to like, share, and drop a comment and telling us your favorite tiny mathematical mystery. See you in the next video.